Okay, we're going to continue on with the presentations here, and the next presentations we have is it's kind of like a panel, I guess. And on the panel we have John Gavloski. John Gavloski is our entomologist for Manitoba Agriculture, and John has been working several years with the department, and John conducts several monitoring programs throughout the province on major insects and pest problems, and also does a lot of speaking throughout the year. So John will be talking about insect resistance. Tammy Jones, our weed specialist for Manitoba Agriculture. She hails from Nepinka, Manitoba. She has a Bachelor of Science in Crop Protection from the University of Manitoba, and she also taught weed identification labs and studied multiple herbicide-resistant wild oats. She returned to Manitoba from Alberta, where she was working in the private industry, and now is, like I mentioned, is our weed specialist. The third panelist is Holly Dirksen. And Holly Dirksen used to work with the department as well, but now she's the Arista Life Science as their technical support specialist. And Holly has spent several years working with field crop pathology, and will be talking regarding disease resistance. So with that, I'm not sure what the plan is as who's going first.
Don't worry, we have a plan. We have a plan.
They've got a plan, so I'm going to let them take it away.
Okay, well, welcome to our talk on resistance management. And with most resistance management talks, you've got a single discipline, either weeds, entomology, or plant pathology. Today, you're in luck. You're going to get all three of those wrapped into one presentation, and then a lively debate on, is there a best strategy for resistance management? Is the entomologist always right? So, and as mentioned, telling us about resistance in the wonderful world of weeds will be Tammy Jones. Holly's going to give us the plant pathology perspective, and I'll be looking after the insect perspective. So,
Let's get started.
So, topics to be discussed. We've got three basic goals. We're going to define what resistance is. We're going to go over 5 ways resistance can develop. And then we're going to look at managing pesticides and crops to reduce the risk of resistance. And is there a right approach that can be taken?
Okay, so pest resistance. I think the key here, because you can all read the screen, I hope. It's a little blurry to me, but maybe it's better to you, is that it's a heritable change. So with pest resistance, it needs to be passed down to the progeny, okay? So for weeds, that's a seed, but for bugs and stuff, it's other things. But it needs to be inherited from generation to generation. And that has to be, that there's been a change in the sensitivity so that what used to be a labeled rate that was effective in controlling that pest, whichever it is, no longer works under normal field conditions. There aren't some extremes that are causing that issue, that it's actually an inherited change year to year or generation to generation, that there's a failure of that pesticide.
So cross resistance is another thing kind of under this same heading, and it's when resistance to one pesticide also results in resistance to another pesticide, even if the pest hasn't been exposed to that second pesticide. So some pests, and we'll talk about this later about what leads to this, but they're just really good at developing resistance to pesticides. So this can definitely happen. We know about it in a lot of weed species where you have weed species that hasn't even been exposed to the second mode of action or active ingredient specifically, and it will have a resistance to it already. So that's important to think about when you're thinking about resistance. It may not just be to one specific active ingredient. And then multiple resistance, and this comes again with those weeds that are really good at overcoming pesticides. So resistance to several pesticides from 2 or more distinct resistance mechanisms in the pest. So it doesn't have to be acting at the same site or the same target. It can be all over in the pest, but basically this is when you have a weed that is not only resistant to one group of pesticides, or one group of
like
herbicides.
11 groups.
Like 11 of herbicides. So those would be example of those species that are really good at overcoming resistance, or overcoming pesticides.
So one of the big questions that often comes up is if we spray a pesticide and we don't kill the pest, is that resistance? And the answer to that's obviously no. There's things other than resistance that can cause a pesticide not to work. Now, one of the concepts we have to be aware of is tolerance. Some pests, whether they're a weed, a plant pathogen, or an insect, they're just naturally tolerant to the pesticide. So tolerance, there's been no genetic change in the organism. Remember, for resistance, you have to have a genetic change that's come about because of repeated spraying. With tolerance, there's been no genetic change. So just to give you an example of this, a lot of people will know that striped flea beetles aren't killed quite as well by the neonicotinoid insecticides as crucifer flea beetle. That is not resistance. There's been no genetic change in the population. In Manitoba, we've got 72 species of flea beetles, and they're not all killed to the same degree by a single pesticide. There's variances. It just so happens that striped flea beetle is a bit more tolerant than crucifer flea beetle, but there's no resistance.
Okay, so other reasons why pesticides fail. I can go on for hours on this one, for weeds anyway, but we tried to shorten it down to just a few. So one of the main issues is a sublethal dose. Now a sublethal dose, so not because of tolerance, but simply we're not getting enough of the pesticide onto the target subject. That could be because of spray coverage, that could be because of weather events, but Holly, back when she worked for us, did this for crop diagnostic school, and I thought it was really cool. So it might be a little bit hard to see, but here's the general thing that I need you to notice. This is water-sensitive paper, which is bright yellow before you spray it with water or anything that's a liquid. And in this case, it was only water. And so on this one, you'll notice that there's lots of blue dots from where the water hit the water-sensitive paper at 10 gallons per acre of water. At 5 gallons per acre, you will notice a significant, sorry, there's the word I'm looking for, significantly less amount of blue on there. Typically, that means poor coverage, and that means less of the pesticide going into whatever you're talking about, unless it's an insect that can actually like crawl over it. So I know you're going to disagree with me, but for me, I really, really want better spray coverage, and I'm not left-handed, so this is very challenging for me. So 10 gallons per acre, at a very minimum, is what I'm looking for in order to ensure that we're getting an adequate dose on that plant. Improper timing, if it's too small, like a wild oat for instance, if it's standing straight up and you spray it, very hard to get to. Sorry, bugs move, things like that too. The wrong tank mix, just not using a multiple mode of effective action, that sort of thing. When it comes to the environment, it could be excessively wet, so nothing's really growing, or excessively dry, so there's a wax cuticle, or it's hard to get through to where that particular target insect is, or target fungus, whatever. Other stress conditions will also impact on the habits of how something grows, and can impact on how much absorption there is into that plant. The other thing is adsorption, which is when a pesticide is stuck on the soil or on the organic matter and it's not available for uptake. Pesticides that are washed off by the rain, new plant growth, and Holly's starting to give me the evil eye. So also improper identification, which for me with weeds, they are so easy to tell apart. It is super, super simple. There's some gray fuzzy stuff and 6 legs, 8 legs. I don't get it all over there. So improper identification can definitely be a challenge for certain pests. And then also extremely high populations. So I've seen soybean aphids at a very high population, or one of my favorite examples is something like Palmer amaranth, where they talk in the States of like 4,000 plants per meter squared. Again, how do you get an effective dose when you have such a high population? I don't know your example.
There are examples for us too, but we'll move on.
4,000 per meter square. We can beat that with insects.
Yeah.
But we're going to now go over 5 different ways that a pest can develop resistance to a pesticide. Well, go to the next one. So the first one we're going to cover is called behavior resistance. And this is one that's actually more specific to insects than anything else. And what behavior resistance is through repeated sprays of, in this case it would be an insecticide, you've selected for individuals that have an altered behavior. And a good example of this is horn flies on cattle. So we'll shift from crops for a second to animal entomology. There's ear tags that you can put on your cattle, and when the cattle move, the ear tags will spread insecticide over the back of the cattle. Now, one of the problems with ear tags is you don't get an even coverage over the cattle. There's more insecticide near the head and on the back than there is on the belly and the further parts of the cattle. Now, what happens with this is over time, you're getting great kill on those flies up near the head and less kill on the flies on the belly. And they've actually been able to select for populations that, given the choice, just naturally go to the belly of the cattle. So behavior resistance, you've altered the behavior of the flies for where they prefer on the cattle.
It's more of an insect thing, given that most diseases and weeds don't have behaviors, I'm assuming?
I only misbehave, I don't know.
All right, so the next mode that we're talking about with the pest is removal. So here we're talking about some examples, gray mold, which are your botrytis species, or tan spot in some cases is thought to have this mode of resistance. And what it is basically the fungicides coming into the cell, and there's some sort of mode within the cell that's quickly shipping the fungicide back out. So you need that fungicide to actually be within the cell and acting on the cells in order to see an effect of the pesticide. So if the fungus has a good way of shipping that fungicide back out and into the extracellular space, you're not going to see the effect of the fungicide. Another one is uptake resistance. So resistant pests may absorb the toxin more slowly. And so this can protect from a wide range of insecticides and fungicides. I think I'm taking John's slide here. Sorry, John. So I know that we have this example in some fungi, but I know there's a lot of insect examples as well.
Yeah, one insect example, the insect on your screen here is the rusty grain beetle. And that is our primary beetle pest of stored grain. So if you've got them in your bins right now, turn on your aeration, get the cold air going through, you can kill them. But a lot of people like to use products like phostoxin, or they used to anyway, when they could readily get them. And over time, what happened was the beetles developed resistance, so they weren't absorbing the phostoxin anymore. It wasn't getting to the target sites in the beetles. So worldwide, there are many populations of rusty grain beetles that are resistant to phostoxin. Not as big of a deal here because we can use cold weather to kill them. So I encourage you, do that instead of the chemicals when you have the chance. You'll slow down your risk of resistance.
Now, metabolic resistance is when resistant pests may detoxify or rid themselves of the pesticide. So basically, the pesticide is coming into the cell, and it's usually by an enzyme action that there's an enzyme acting within the cell, breaking down that pesticide quickly. And basically, almost all cells have these enzymes, but some fungi or weeds just have more of these enzymes, or they act more efficiently, so it happens a lot quicker, and that's when you would see a reduced effect of the pesticide and would talk about resistance. So it can either be through this breakdown by an enzyme, or in some examples, which I think is this glyphosate-resistant Canada fleabane, it actually packages it into a vacuole, which is kind of like a closet in the cell where you hide things.
You just put it in a garbage bag and set it aside.
So because it's in that vacuole, it's not able to have the effect on the cell.
Okay, so the one that I most frequently encounter with weeds would be altered target site resistance. And there's two different ways that altered target site resistance can happen. So this is a diagram that is also applicable to some insects and to some fungi, I don't know, fungal stuff. And what actually happens is that you have a target site that could be a particular shape. And typically, the function of that works well. When you spray it with a pesticide, it makes that function not happen anymore, and then something dies. When the target site is altered, that binding at that target site can no longer happen, and therefore whatever that pesticide was is ineffective. So this is fairly frequently found for a couple of very important groups of herbicides. So group 1 and 2 herbicides, we see resistance develop very quickly to them, very few number of applications. Now I'm not sure, is it the same thing for insects and fungi? Is it a quick thing or altered target site?
Definitely the fungicides that are more susceptible to this type of resistance developing are ones that are sprayed more frequently, so it's hard to measure whether it's a quick thing because of the type of resistance developing, but also just the quantity of fungicide that's going down.
And with insects, frequency is a big one. If you repeatedly use the same group over and over on a pest, you increase your risk of resistance.
Okay, so the second one is altered target site, and this was my version of it. A little bit challenging because I am not an artist, but here we try. Okay, so you got the same function happening in a normal pest, whatever it is, and then in the one where you're seeing the gene amplification or overexpression, instead of that herbicide, pesticide, insecticide, whatever it is, being applied and no longer binding to that site, there's just enough of that enzyme or target site, whatever it is, in the plant that it inactivates the herbicide, and then the plant keeps functioning because it has 20 copies in kochia, 160 copies in Palmer amaranth, whatever it is, to be able to overcome whatever dose of pesticide that you actually apply. And so those are my examples.
Okay, looking at the ways that pests develop resistance to pesticides. So we've seen 5 basic techniques that they can use. With insects, they can use basically all 5. And some insects do. Colorado potato beetle would be an example of one. There's been reports of behavior resistance, altered target site, pesticides not able to be absorbed. Basically, some insects can do it through multiple ways. Whereas it's a little different with weeds and pathogens. They tend to be more resistance through altered target sites.
John's a show-off.
So, bugs are better in many ways. So.
He keeps trying to tell us that. Okay, so there are various things that contribute to the development of resistance, right? So in addition to the target itself, the pesticide characteristics and the crop characteristics that are the host crop, I guess, would be other things that impact on how that resistance is developed.
Right, so first we're going to talk about some pesticide characteristics that are more likely to lead to pesticide resistance. And one of them we kind of talked about with this target site is whether the pesticide is single site or multi-site mode of action. So again, we have some more puzzle pieces up there. We love our puzzle pieces here. And the idea here is for a single site active, so that's on your left, there's only one piece of the puzzle that fits. So you need that puzzle piece to fit in order to see the pesticide be active. Whereas when you have multi-site on the right there are actually 3 places where that pesticide can fit into the puzzle and cause the pesticide to be effective. So if you only have one site, you only need one genetic change, one genetic mutation, and then that pesticide is no longer active. Whereas when you have multi-sites where it can be active, one genetic change isn't going to have a huge effect.
Okay, so then also the level of exposure is something that can be an impact on the development of resistance. So that could be a number of different things. That could be repeated applications. I mean, we all have examples where repeated applications, sequential selection, whatever you want to call it, ends up in resistance. And one of the easiest ways to have repeated applications is to have large acreages that are given that particular pesticide, whatever it is. And I think the example that jumps to mind for everyone is glyphosate. It's applied everywhere all the time, which isn't exactly true. But at the same time, there is a large number of opportunities to utilize a very effective herbicide, and that does impact on the level of exposure. The other thing there that can be an impact would be how long that particular pesticide persists for, right? So, and that can effectively be the same as repeated applications because you have something that lingers longer, continues the selection pressure for longer. The application rate, that's very important when we're talking multiple modes of effective action, which us weedy types try to fit in there all the time. Doesn't necessarily apply with everything else, but for those multi-site mode of action pesticides, if you don't have the right rate, say that 5 times fast, everyone. No, I'm kidding. Then it's very challenging to control that and ends up in a sublethal dose. High rates can control something that has an intermediate level of resistance, really. So sometimes upping the rate can help. More often than not in weeds that isn't the case, but sometimes in some of the other targets it can be.
So we've mentioned earlier about repeated applications of insecticides are what can lead to resistance. But when we talk about repeated applications, we're focusing more on insecticide groups. At least with the insecticides, we're focusing on the groups. So for somebody who's growing potatoes and you get resistance to potato beetles, switching between malathion and lorsban isn't doing you any good. If you've got organophosphate resistance, you have to go to another group, not another product, another group. And we do have resources available to help you with those choices, but keep that in mind with the insecticides. The group is what is important.
That applies to fungicides too.
It applies.
Yeah.
It applies.
And for fungicides, I feel like, now with insecticides, things like neonics, we're starting to maybe more understand the groups and talk about, groups as a wide range. And in herbicides, for a long time, we talk about group 1, group 2. Nobody knows their fungicides groups. So that's my goal.
You have groups?
Yeah, my goal is to teach people their fungicide groups and keep that in mind. So this was a triangle that it's kind of modeled after the one from the Weed Science Society, and it's done by Christina Polzin out of Alberta, but it talks about the groups of fungicides and which ones have the higher risk of resistance developing. So I'll just talk about the top 2 there, group 4 and group 11. Right? You all know what that means because you've been studying up your fungicide groups. So group 4s, we don't have a lot of foliar fungicides, but group 4s is your metalaxyl, which is in a lot of seed treatments, almost all seed treatments. Good job, Tammy. So that has a higher risk of resistance developing. And then your group 11 are your strobies. If you don't know what those are, look in your guide to crop protection.
Okay, so this is the one that most people are most familiar with because Hugh Becky developed this back in like 2006, so it's been around for a while, and that's why it's there. And it gives you an idea of the amount of risk associated with a high number of applications and the risk of developing resistance. So something that's a high, a 1 or a 2, it takes less than typically 10 applications before the weed has selected for resistance. In something that's low, we don't mean it's never going to get resistance because we've proven it wrong with everything already, but it takes a lot longer. So for instance, if you look at the group 4s for us are like your 2,4-Ds, your MCPAs, the auxin mimics, and it's taken a lot longer to develop resistance to that, although there are cases of that as well. And definitely everyone knows what group 9s are, glyphosate, and that there's resistance to glyphosate. So just because it's a lower level, it just means that you need to have more applications in order to likely select for resistance.
We're going to switch tracks here from pesticide characteristics that can lead to resistance to pest characteristics. And just to reinforce what we've covered earlier, genetic diversity is one of the things that in a pest can lead to a higher probability of resistance. If you've got more individuals in the field, you've got more genetic diversity out there, easier to select for some resistance. And there's other things that can contribute as well. We've got some pests, some insects and diseases mainly, that blow in. They're not things that overwinter well here, they blow in annually. And we can essentially end up inheriting problems that have developed in other areas. So that can happen. Good example of that, soybean aphids. In 2017, we had really bad soybean aphid problems. We actually were able to document resistance in the Manitoba population. I'm convinced that that is not the fault of Manitoba growers. They hadn't been overspraying. The past few years prior to that, we didn't have soybean aphid problems. Growers weren't spraying. But they were spraying back in the areas where soybean aphid successfully overwinters. In fact, some of them do it almost annually because they overwinter there and they're just wanting to prevent a problem. Preventing the problem can sometimes lead to a worse problem.
Just so you know, weed seeds blow too.
And weeds, sorry, Tammy. Don't want to leave that one out. They do blow in the wind, and tumbleweed, and yes. Not to leave Tammy out. But one of the points I was trying to make here is genetic diversity is key. We can inherit it from other areas, or we can get it here through just big populations that you overspray.
So some crop characteristics that now lead to resistance, and we kind of touched on this already as well. But one of the things is limited chemistries and control options. So definitely for some of our smaller acreage crops and even some of our bigger acreage crops, there's sometimes just limited mode of action that's available to spray on that particular crop, for use on that crop. So that's when something like varietal resistance really becomes of the utmost importance, because if you only have limited chemistry, you really have no choice, and you're increasing your chance of resistance. So you want to make sure that you have good agronomy to start with, which we're going to talk about later, with something like varietal resistance. And then we talked about the crop being grown on a large acreage. So glyphosate-resistant crops, but even something like canola, that's maybe you're a grower that sprays every year for Sclerotinia, or on wheat acres, if you're a grower that sprays every year, and a lot of growers do, for Fusarium, that's a better chance that you're building up that chance of resistance. And then also when crop is grown on short rotations, so maybe wheat and canola would be an example there as well.
Canola,
perhaps.
snow canola, that one?
Okay, so now the big question, can we take an integrated approach to resistance? So we've seen there are differences in the way the three of us would approach resistance management. And I'll start off with the insect perspective here. We do encourage what we call integrated pest management as a way of reducing your risk. Integrated pest management means basically doing things to pesticides are part of it, but doing things to minimize the amount of spraying you have to do. So using economic thresholds, scouting your fields, cultural controls, resistant varieties, they can all contribute to reduced use of insecticides and pesticides in general through good IPM programs. That reduced use of the products is going to be key to reducing your risk of resistance.
Okay, so the Aphid Advisor one was the first example. You're going to have to click again there. Okay, so this is one in wild oats. Do you really have to always spray your wild oats? And this you can find in the Guide to Crop Protection if you can't read it up here. But it's simply just saying, make sure you know how many weeds you have there before you start spraying for them all the time. This whole, I don't want to have them growing by the roadside because my neighbor's going to point at me and laugh. That's not the best way to justify whether you do a weed control action or not. So we have an economic threshold that makes sense, dollars and cents to you, but also mitigates your risk for resistance development.
Now, from the disease perspective, it can get a little more complicated. Generally, we're not out there counting something because you want to be spraying your fungicides before the disease shows up.
Counting spores, I love it. Go for it.
Which, I mean, there are out there. There's now those spore metrics where they can, catch spores on the wind and figure out whether there is a risk of a disease showing up. But another way we look at it is just from the environment. So I don't have the disease triangle on there, but everyone can visualize a disease triangle in their mind. So you have your host, you're growing your host, you have that. You have the pathogen, is it present? For things like Sclerotinia and Fusarium, we assume it is always present. So the big question becomes the environment. So this is the Sclerotinia treatment decision tool that I pulled off the Manitoba Ag website. It was developed a few years ago, and it basically just puts in your risk points based on the conditions that are there. And I think do we have two here? Yeah. So just showing when your risk is low versus when your risk is higher, and it tells you likely beneficial to spray, and it's all dependent on these different factors that are in there. So not necessarily an economic threshold the way you would think about it with insects, but provides the same kind of guidance.
Okay, can we take an integrated approach? Yeah, sure, we can-ish, maybe. We need to start with good basic agronomy for everything and apply the full labeled rate at the right stage. Now, these guys talk a lot about rotation of pesticides. Sure, it's nice. Kind of slows things down a little bit for resistance for herbicides, but doesn't really negate the development of resistance in weeds anyway. So I don't know if you guys just don't spray as often as I do or whatever the problem is, but for us, rotation isn't quite enough. We're going to want you to apply multiple modes of effective action. And I'll be honest, that doesn't mean throw in some MCPA and hope that that's going to kill your wild oats better, because that's not an effective action on that particular target weed. So when I talk multiple modes of effective action, I mean multiple different types of chemistries that will kill the target weeds. That could get a little expensive in some of the mixes, but I mean, you could hand weed if you'd rather. And then the other thing that we talk about as a way to get that multiple modes of effective action when you can't get it all in the same tank is to go with layering. So that means maybe doing a pre-seed that has some extended control and then going in with something else that has a different mode of action that will still kill that target weed if there's still some left. And we found that we get much superior weed control when we go with a layering approach rather than just trying to throw everything in one tank and hope for the best, because it just is a little bit more challenging for spray volume and all that jazz. And once you throw in some fungicides and some insecticides, you could probably make glue.
I just want to jump in too, because I think that in fungicide world, it is starting to move towards these multi-mode of action in one product as well. And so then the same thing comes back. It's the multi-modes of effective action. So are the modes that are in that multi-mode product actually targeting the pest that you hope you are targeting in your field? It's something to think about as well. So another thing to talk about is taking advantage of natural enemies of potential pests. Obviously, this is something...
Rabbits. We grow lots of rabbits.
Yeah, something that applies primarily for insects. So when you're out there doing your counts, be also looking at the beneficial populations before you make that decision on whether or not to spray an insecticide. And then this avoiding the prophylactic use. So this probably applies more to John and I in the insecticide and fungicide world, but it basically making sure that you actually need to spray the pesticide before it's out there. So it's out there looking at your economic thresholds, looking at the environment. I've had people tell me that they just spray for Fusarium every year. If it doesn't pencil out this year, it's going to pencil out, in 10 years, because I'm going to spray every year, and the years when it's worth it, it's really worth it. And I get that on the pencil and paper, that's how it looks, but when it comes to resistance, it's something else we need to be thinking about. So even when it's not a really high pressure year for certain pests, there is a number of the pests that are still present and maybe isn't causing you a yield loss, but the population is there, and if you're spraying, you're adding some more selection pressure on selecting for pests that have the resistance to that pesticide that you're spraying.
So I saw the side eye from Holly there about prophylactics, and I think she means pre-seed herbicides. Knowing your field, knowing your previous year, what kind of weed pressure you had, will help you to assess your economic threshold for utilizing that pre-seed herbicide in the next year.
You have no idea what my side eye about prophylactics means.
Keep going.
Okay, so resistance management is obviously one reason to only use pesticides when you need to, but there's other repercussions as well. Every spray you do has its potential benefits and its potential risk to it, and that's important to consider. Some entomologists in the US decided to do an experiment. They wanted to see if they could create a soybean aphid population explosion by spraying fungicides, not insecticides, fungicides, and they were successful. So what they did was they did basically prophylactic sprays repeatedly in some of their plots, and they were able to create a soybean aphid explosion. And the reason they were able to do that is fungi can be potentially bad things for crops, but there's also good fungi. And one of the ones that I have featured up here, Pandora neoaphis, that's one of your fungal superheroes. Because what Pandora neoaphis does is it infects aphids. The name neoaphis, it affects just aphids. So it's a fungus that likes attacking aphids, and when there's a lot of it around and you get the right environment conditions, they can keep aphid populations low. If you are doing repeated fungicide applications and you're wiping out these good fungi, that gives the aphids a chance to explode. And that's what happened in this case. And just as a side note to that, Neozygitis floridans, that is another fungal superhero. That one attacks spider mites. The same scenario plays out. You can create spider mite problems by overusing fungicides. So plan your strategies accordingly. Use insecticides when you need to. And remember, there's always benefits and risk. You got to figure out which is the greater.
Okay, before you two start a fight, I'm going to just, let's maybe start with an example. Let's try a crop rotation. So we're starting with good agronomy, and there's some crops that are more competitive than others, which for me, for a weed control perspective, is going to help me out. So let's play along for a little bit with helping me out. Fall rye, winter wheat, those are great because they get a head start on the weeds, but they don't fit into every crop rotation, so let's try an annual. I mean, barley's quite competitive, but I think you get bigger bang for your buck with wheat these days. So if we take wheat as the example, for a couple of reasons. So return on investment as far as what you grow, but also it has the most weed control options. So for me, wheat. Can we agree that wheat's a good crop that we could try growing in a
good rotation?
In a good rotation of 4 different crops.
Okay.
3 or 4? 4 of 3. Okay. Okay, so I was scrolling through the new Seed Manitoba, and yeah, I live in southwestern Manitoba, or I used to, so I picked Wasquita.
Near and dear to your heart.
Yeah, and also it's super tall, so I wanted a nice height, and yeah, yield was decent, like moderate, so that for me, I'm picking Wasquita. Anybody?
Any comments, John?
She probably also picked it because it has mild resistance, oviposition resistance to wheat midge.
I'm sorry, what?
Which would be wheat midge. Think bugs
Okay,
when you're making
sure.
your decisions as well.
I'm okay with Wasquita. It has an MR for head blight, which for your spring wheats, that's as good as you're going to get. It doesn't have as good of a resistance package maybe as some other varieties when it comes to other like things like stripe rust, but I'm okay with it. You also have a circle around Shaw.
Well, that wasn't for me.
Oh, this is John
Shaw is great because it has really good resistance to wheat midge. So if it has a VB after the name, that means it's got a very high level of midge resistance. Wasquita's got I'll call it a low to moderate level. Shaw, anything with a VB is really, really good. So if wheat midge is a concern, that's the way to go.
Okay, and I can see how Shaw would be all right because it's a tall one as well, so it'll help me with shading out those weeds. So I could go with Shaw.
I do not like Shaw, however, because Shaw is an MS for Fusarium head blight. And in those years where you don't have a lot of pressure for Fusarium, I want you to have good resistance so that you don't need to be spraying a fungicide, which will select for resistance in your pest population.
Okay, how about seeding rate? Can I talk seeding rate for a minute? We'll figure out the variety in a minute. Okay. I want to double the seeding rate. And not just double it in the row, but I want to cross seed it so that I'm getting shading like you would not believe.
Sure, shade is okay, but that also really increases the amount of moisture that's going to be held in that canopy, which is basically important for every fungus to thrive. So yeah, a lot of shade, but then you're going to have a great environment for all the diseases. Keeps me in a job, it's fine.
I think John agrees with me. Look at him.
Well, higher seeding rates are good. If you seed too light, what you will get is more tillers, which means a longer flowering period, which means more risk of wheat midge. So
I feel like I'm outnumbered. I might just have to quit.
Okay, so I think what we're trying to say is that it's really not that easy on your farm for us to be able to tell you what works. You have to know what works. There's a lot of things to take into consideration. One of the ways that the professional side of life, the non-farmers, try to help monitor and mitigate for resistance is through things like field surveys. So I'll go out and actually take samples, market research surveys where your opinion is asked, or by tracking performance inquiries. And that's really helping us to understand and make sure that we enhance the awareness of the scope of resistance and then try to develop some BMPs. And I think we still have some fights amongst us as far as what those BMPs might actually be. The other part of this is that by early detection, we can start to help mitigate the spread of the problem. Let's be real. We're never going to eradicate it because it's going to blow in or redevelop in the area. So eradication is probably impossible, but early detection can help us to mitigate the risk.
So we've been talking a lot about pesticides and whether or not you rotate groups or multi-layer. There's some great resources out there for you to look up the information that you need. With insects, there is a group called the Insecticide Resistance Action Committee. You can Google that. It lists all the different groupings of insecticides. It tells you what's in each group, the mode of action, how it works, so you can use that as a guiding tool. There's similar resistance action groups with fungicides and weeds. So again, the websites are all there. Take advantage of those. And then there's our Guide to Crop Protection. And we do list our groupings in our Guide to Crop Protection. If for the insecticides, go to the front of the insect control part. It's right at the front. We have all their groupings, and you can pick the ones that are most appropriate.
We're running out of time. Next slide.
So resistance management requires long-term planning. Here's a quote I really like. This is from Fred Gould, that in the economically competitive environment of agriculture, the general orientation is towards short-term profit, whereas the concept of resistance management emphasizes long-term payback. So the key there, resistance management, you're looking for the long-term paybacks.
If you're not farming for the long term, you're not farming long.
And then this is, I mean, the message that we want you guys to leave with is there's no single resistance management plan, and that's not even just for an individual farm. There's no single resistance management plan for an individual field or an individual pest within that field. So you might have different plans based on your weed population. It's about figuring out what you need to do in that particular field and the best way you can mitigate resistance in the long run. That's everything.
Any questions for John or Holly?
Everyone's just hungry.
I am too.
Yeah.
Silence.
Good. Thank you.